Hello, my name is Nishan Chatterjee, and today we're going to look at the LeetCode coding problem called Swimming in Rising Water. First, we're going to look at the problem description and give an example, actually two examples. Then we're going to look at the priority queue solution, give an explanation, an example in the code, and we're going to do the same for the binary search solution. Then we're going to analyze the time complexity of both the solutions. Here's a problem description. You're given an n by n grid, and each square in the grid resembles the height or the elevation at that point. It starts to rain, and at time t, the depth of the water on every square is t. You can swim anywhere where the elevation is at most t, where the water has reached that place. You can swim in any four-directional adjacent square. You start at square 0, 0, and you can swim in infinite amount in 0 time, and you have to find the minimum time to reach square n minus 1 and minus 1, or the last square, bottom right. Looking at this example, we have 0, 1, 2, 3. So we first either go to 1 or we go to 2. At time 1, we can go to 1, and then we have to wait until time 3 before we can go to 3. So the solution will be 3. Looking at another example, a slightly bigger square. At time 1, we go to 1. At time 2, we go to 2. Time 3, we go to 3, and so on. And then we wait until time 16 before we go to square 16, and then we swim all of this distance because time 16 already passed, and all of these numbers are less than 16. Now let's look at the priority queue solution. You might have noticed that the answer is the least maximum number on any path. That means of any path you can choose, the path that has the maximum number minimized is a solution. So how we implement this into our solution is we keep a min priority queue and initialize it with the origin square, and then we keep popping from the queue, and every time we pop a number, we add all of its neighbors to the priority queue. We also store a maximum variable to hold the maximum number we found. This works because the priority queue ensures that we only look at the smallest numbers. Let's look at the previous example. The priority queue contains only 0 since that's the origin square, and the maximum number is 0 because we only looked at the origin square, which is 0. Now we add the neighbors 1 and 24 to the priority queue and pop 0. Now since 1 is the smallest out of these, we pick 1 and add its neighbors, which is 2 and 23. The max updates to 1 because 1 is greater than 0. Then we add 2 since we pop 2 since it's the smallest, and add its neighbors, which are 22 and 23. We do this for 4, or for 3, and we add its neighbors, and so on. Now let's look at the code. We have the initial driver method. We create this class called trio, which holds 3 numbers, nothing else. We use this in the priority queue, which you'll see in a bit. We use the variable n to store the grid.length, so we don't have to call it every single time, and res, which is the final answer, or the maximum variable that we talked about. We initialize a priority queue of trios and have the comparator compare the first variable. The priority queue resembles the value at that grid location, the x and the y coordinates. We add the origin number, which is grid at 0, 0, which is the value, and 0, 0, which is the x and y. We also keep a Boolean array, a 2D Boolean array, called scene, to check which numbers that we already visited. I also have this array called directions, which resembles every direction you can go in. We will use this later. We loop until the priority queue is empty, which will never happen if there is an actual solution, but I'm going to do it anyways to prevent null pointer exceptions. Now we pop the top off the priority queue, stored in a variable called top, and update the maximum variable using math.max. If the coordinates are already at the end, then we found our answer and returned the maximum variable. Now for each direction, we check if it's out of bounds if we go in that direction, and then we add that neighbor to the priority queue. Also, we add true to visited that neighbor. Outside of the loop, we return -1, but we know it'll never reach there. Now let's look at the binary search solution. Another solution you might have thought of at the beginning is doing a linear scan of every single time and then checking at every time if we can reach the end. In this example, you might check through 1, 2, 3, 4, and then reach 16 and realize at time 16 you can reach the end, so you turn 16. Obviously, this is very slow, but we can optimize it because we use a linear scan, but an optimized version of linear scan is binary search, so that's what we're going to do. We binary search every possible time by keeping the high as n times n minus 1, which should be the last number, and the low as 0, which is the origin. Every time we reach a new element, we use either DFS or BFS to check from the beginning if we can reach the end. Let's look at an example. We keep the low as 0 and the high as 24, since the highest number is 24 in this grid. The mid would be 12, because 0 plus 24 divided by 2 is 12. We see that using time 12, we cannot reach the end in any way, so we raise the low variable. We raise it to mid plus 1, which will be 13. Now the mid is 18, and we see that we can reach the end. So now we lower the high variable to mid. The new mid is 15. We see that we cannot reach the end with 15, so we raise the low variable again to 16, which is 15 plus 1. Now at 17, we see that we can reach the end, so we lower the high variable. And now we see that low and high are equal to each other, so we stop and return 16 as our answer. Now let's look at the code. We have this driver method. We initialize low and high, and also n, which is equal to the grid length. We keep a loop for while low is less than high, and we also store the middle variable, which is low plus high divided by 2. We keep a visited array, which is all the elements that we already visited, which we'll use when calling the method to check if we can reach the end. If we can reach the end, which is called by this hasPath method, then we set high equal to middle. Otherwise, we cannot reach the end, so we set low equal to middle plus 1. Outside of the loop, we have finished, so we return low. Now all we have to do is implement the hasPath method. We can either use DFS or BFS starting from the start. I chose to use DFS, but you can use BFS if you want. It doesn't really affect the time. So first, we check that if we reach the end. If we reach the end, then we return true. We can reach the end. Then we update the visited array by setting the current element as visited. And we have the same directions array from before. And we check each direction and call DFS of that direction. We also include a number of checks, including if that neighbor is out of bounds, if it is visited, if the time is correct, and then if it is, all of that is true, we return true. Otherwise, we return false. Now let's look at the time complexity of both solutions. In the priority queue solution, the priority queue will take at most n squared elements. Note that n would be the length or the number of rows of the grid. It'll take n squared elements because at worst case we add every single square to the priority queue. A priority queue most optimized runtime is O of log n. And the pop will be called n squared times at worst case, because at worst case there are n squared elements. So the time complexity of the priority queue solution is n squared log n. Now let's look at the binary search solution. Binary search takes O of log n, and the DFS or BFS takes O of n squared, because at worst case you look at every single square. So log n multiplied by n squared is O of n squared log n once again. So the time complexity of both solutions is O of n squared log n. Thank you for listening, and I hope you enjoyed.